have this dimension technique. So you can sit down. Thank you. The last talk, I think, is going to Sky the session back to Multigroup.
Yeah, so this is the last talk of a long workshop. So thanks for sticking with me. This talk is going to be about multi-calibration in the covariate shift setting, so similar to 2 days ago when Christoph talked. And it's going to be about when it's both robust, but also in some ways targeted and optimal. I guess I should say I'm David Bruns-Smith. I'm a computer science PhD student here. And these are my lovely advisors and collaborators. We have Avi, who's here, Emmy in the economics department, and then two really wonderful collaborators who have been Betsy at Johns Hopkins and Oliver at Ghent, who have contributed a lot. Okay, so I'm going to talk about two broad approaches to correcting bias that comes from covariate shift. So I'm going to be thinking about a setting where we have some training data. We're back to XY pairs from some distribution P. But then in our test distribution Q, we face some type of covariate shift. And I'm going to focus on the setting when we're interested in just estimating this scalar estimand, the mean under the test distribution Q of the outcome Y. And this shows up in all kinds of problems. So I came here from causal inference. This also shows up in fairness applications when you're looking at subpopulations, and it shows up everywhere in offline reinforcement learning. So the two approaches I'm going to be comparing are this sort of universal adaptability target independent approach where you fit one predictor in the training data. And if it's multi-calibrated, then you know it works well for any target Q. So this is a really nice robustness property. A different approach is if someone tells you what your Q is beforehand, you can go do some type of targeted estimation for that particular distribution Q to get something that's more optimal for that single target distribution. And the punchline of the talk is going to be that there are settings where there's no gap between these. So we're going to connect the two approaches with this sort of very simple algorithm, which is we get some training data with XY pairs. We fit your favorite ERM predictor, F hat. And then you do one auditing stage where you do one step of boosting with ridge regression to get a multi-accurate predictor, F hat M. And then you just plug that in on your test distribution. And it turns out that this is numerically identical to a procedure from causal inference called augmented balancing weights. And this procedure has all sorts of really nice theoretical optimality properties for a particular target distribution Q. So what do I mean by that? Oh yeah, go ahead. You take your F hat of M, and then you take some X samples from Q and just calculate FM hat XQ. I'll be more specific about that in a bit. Okay, so the takeaway is that this simple multi-accurate predictor is not just robust, but no matter which Q you plug it in, subject to certain conditions, it's going to be optimal on all of them. And it's because this procedure that this multi-accurate predictor is numerically identical to turns out to be semi-parametrically efficient. Go ahead. We only after are you using? Yeah, that'll come up much more cleanly in a bit. That's a great question. Because that's kind of what makes this so weird, is that you don't see Q, and yet you're simultaneously, by using multi-calibration, semi-parametrically efficient for Q. And this holds in a special setting where your auditor class belongs to a Hilbert space. So this includes some nice algorithms like ridge regression, kernel ridge regression. We're going to show that it holds for random forests with a little bit of extra work. Doesn't hold for L1 type spaces. So lasso is not going to have the properties that I talk about. Okay. Lots of related work. Unfortunately, there's just two. Both the multi-calibration literature is big, and the semi-parametric literature is really big. So it's hard to review, but the most directly applicable ones that I'm interested in are going to be this universal adaptability paper, which talks about how multi-calibration can make you robust to covariate shift. And if you want a primer on all of this, like doubly robust, the title is so funny, semi-parametric, doubly robust, targeted double machine learning, a review, gives a nice primer to, like pulling together these different perspectives on the same problem. Okay, so to be a little bit more precise, we're going to assume that we have some training distribution P. We see some XP and YP draws, IID. We have a test distribution Q, but our YQ is missing. So this shows up when you're trying to estimate an average treatment effect in observational causal inference, where this would be the treated group. Our estimand is going to be the missing mean under the test distribution. And we're going to have to make one assumption, which is that the conditional distribution of y given x is the same in the two groups. So in causal inference, we call this no unobserved confounding. In biostats, it's called ignorability. In computer science, it's called the covariate shift assumption. But this is what I mean. OK, so one typical procedure would be just use ERM, fit f hat using p, and then just plug in. So this is what I mean by plug-in estimator, where this is empirical sample average. And the issue is that because you trained in P and plugged in Q, you can actually face pretty substantial selection bias, so that this estimator can be pretty poorly behaved. OK, so one idea which shows up in the multi-calibration literature is that you try to be robust to many shifts. You try to fit an omni predictor across all of these different DQDPs. So you assume that your density ratio, DQDP, belongs to some set C that includes C1, C2, C3. And then multi-accuracy over this set is going to ensure some type of small bias property. So here's the definition of multi-accurate. It actually hasn't come up in the last couple talks, so we're going to refresh. It's when the worst case average reweighted residual is small. And in particular, yeah, that's right, that's right. To make it multi-calibrated, we have to stick the f hat in here, which for the purposes of my talk, for the numerical results, doesn't make any difference. But in practice, if you think about covariate shift that can adapt to the estimator that you're using, in practice, this is a big difference. But because I'm working with numerical results here, I'm just going to say multi-accurate, but multi-calibrated is fine. So what do we get from multi-accuracy? We get this universal adaptability property, which is if we're multi-accurate with respect to this pile of density ratios, then we're approximately unbiased for Q1, Q2, and Q3 when we just plug in f hat m. So this is this really nice property, and it has this sort of well ordering. You only train on P, you don't get to see Q, throw it at any Q in it. It's going to at least be approximately unbiased. OK, so that suggests this meta algorithm, because one way that we know of how to get multi-accuracy is by doing auditing. So if we have our set C of density ratios, we can audit with regression to get f hat m, which is then multi-accurate, and we plug that in on the test sample. And this is the basic meta algorithm of the universal adaptability paper that Christoph alluded to 2 days ago. OK, is everyone with me? All right. We're going to specialize this to a very theoretically nice function class, which is Hilbert space balls, which have lots of really, one of the best things about them is stuff has numerical closed forms, which is really, that's a dream scenario. But we're going to be thinking about our points x that belong to a Hilbert space defined by some inner product. And we're going to be thinking of C as being a collection of functions defined as Hilbert space inner products. So what would auditing over a Hilbert space ball be? It's ridge regression. So I've written it in the familiar finite dimensional form, but you can think of these as infinite dimensional matrices, and everything's going to go through fine. So this is actually a pretty big class of algorithms. But if at any point you're grasping for intuition about what infinite dimensional regression would mean, just think about ridge regression. OK, so this includes ridge, kernel ridge. Actually, random forests are just a special case of ridge regression, but where the basis is adaptively chosen. The adaptability actually will break our numerical results, but it turns out you can separately prove that it holds for random forests, which is nice. And it also has been a sort of fertile ground for theoretical research on neural network generalization with interpolating estimators, which if I get to the end of the talk, we'll talk about more. OK. So I'm going to say that we are going to do this sort of really, really simple procedure. We're going to fit f hat with ERM, just like you would for universal adaptability. Then you're going to fit ridge regression on the residuals. So this is boosting. It's like an auditing procedure, except it's the stupidest kind. We just run regression once. The implied ball C that we're trying to be multi-accurate with is a Hilbert space ball. That's just the meaning of ridge regression. And then we're going to form our new predictor with just this one stage additive boosting. And we're going to plug that in on Q. I'm going to claim that this thing is multi-accurate, although you'll notice that this doesn't have the form of MC boost. So I can't use the universal adaptability paper off the shelf. But it turns out we can still prove that this simple once boosted ridge procedure is multi-accurate. And hopefully I'll get to talk about that at the end, but I want to get through the main results first. So this is somewhat abnormal. There's no exponential weighting here. You're not running it multiple times until convergence. Okay, so before I can actually give you my main result, I need one extra technical result. Fortunately, it's really cool, and it's just about ridge regression. And it's that ridge regression just happens to estimate density ratios. This is a really strange fact. One fact that many people know, and in fact, like in my experience, learning theorists love to show everything's a linear smoother. But ridge regression, if you fit ridge regression in P and then just plug it in on XQ, that's equivalent to some linear smoother on the YPs, which is some function W hat applied to the XPs. So ridge regression applied to Q can always be written as a linear smoother. But W is not just some random function. W solves what in my corner of causal inference we call balancing weights between P and Q, which is kind of related to standard propensity score estimation. It's a bit of a different flavor. But basically what it's doing is it's an empirical analog of least squares for the density ratio. Where the key point is that the function class that we're minimizing this least squares problem over is a Hilbert spaceball. So at least this was very surprising to me when I learned it, that you just fit ridge regression, plug it in on a target distribution, and really what you're doing is like implicitly fitting a density ratio model and then transferring your outcomes from P to Q. But this equivalence is going to give us some really nice properties. Oh, I have a technical omnibus, which is not about multi-calibration, but is about this style of result that actually is going to be announced on arXiv on Monday. So look out for this paper, Augmented Balancing Weights as Linear Regression, if you're curious about this style of result in causal inference land. But this gives us something really neat when we apply it to boosting. It basically means that boosting is this simple one-stage boosting procedure is going to implement bias correction. So we have our F hat M, and just as a reminder, F hat M is our original ERM plus this ridge regression from ridge regression on the residuals. That's this right-hand term. And I just told you ridge regression, when you plug it in on Q, is the same as an estimator for the density ratio. So we're just going to plug that in. So we get our base model, and then we get this W hat times the residuals. And if you, well, wait, where W hat belongs to the Hilbert space. And if you remember, this W hat is a least squares approximator for dq dp. So this whole term is a bias correction term. You have the error, your training error under P, which is YP minus F hat, and you're reweighting that to look like what the error should be under Q, and that's getting subtracted off from this biased estimator. So you plug in the biased estimator, and this boosting step unbiases it for you. So does this make sense? This is the sort of algorithmic numerical equivalence of there's this multi-accurate procedure that is doing this debiasing for you automatically. Okay, so what do we get from that? And this meta algorithm where you fit W hat with something called balancing weights is called augmented balancing weights estimators. This thing where you do this boosting procedure and it turns out to estimate the density ratio is true for ridge, but again, it's not going to be true for lasso. So this is at least a little bit of a special case. You can't just regress on the residuals with literally anything you'd like. Okay. Fortunately, we have this numerical equivalence to this estimator that people have studied to death. So this estimator has actually been rediscovered many, many times. The survey sampling literature calls it GREG, and it comes from at least 1992. In causal inference, it's been called augmented minimax linear estimation, because actually that density ratio problem can be written in a minimax form. It's been called approximate residual balancing. That's more my style, where I call it balancing weights. And then it was rediscovered in econometrics, where it's called automatic debiased machine learning. So you might have heard of debiased machine learning. That was the first Chernozhukov paper on this. And then he has another one that's called automatic debiased machine learning, which is this estimator. So we have this numerical result. Ridge boosting gives you this augmented balancing weights, and you get this lovely statistical result, which is that if we have this sort of a well approximation of the ridge, giving us dq dp is in h, and so we actually are converging to the truth. And if our f hat is a sufficiently good predictor to begin with, it can't just be junk, you get semiparametric efficiency. So here's just two examples of proofs of this type of thing in Hilbert spaces. What does semiparametric efficiency mean? It means that we're optimal in the sense of achieving some type of variance lower bound. If you don't like asymptotics, there's also nice non-asymptotic results, like this paper from Berkeley, for example. So if you don't like asymptotics, you can believe me that this is still a good type of result to get. This is one thing that I feel like is a little bit underappreciated amongst computer scientists, but you get an asymptotic normal confidence interval, which is really nice. It means you do your plug-in estimator and you just get the easiest, just calculate your standard errors and you get a nice uncertainty quantification estimate. And in particular, ERM plugins will not give you a valid asymptotic confidence interval. So this is just a nice, this is the bonus. And again, it's not a bonus if you don't like asymptotics, but it's something that you can compute to put in a paper with standard errors. And also, more agnostically, we don't necessarily need dq dp to be correctly specified in the Hilbert space, as long as we get like things are non-parametric enough and we can estimate things at a sufficiently good rate, you're still going to get efficiency. And that's discussed at length in this paper, Orthogonal Statistical Learning, which maybe is more familiar to this audience. I'm not sure. Doesn't look like it, but yes, finite sample everything. So it could be nice. All right, so let's summarize. What do we show? We show that you fit this W hat, this F hat M, which I claim is multi-accurate. It's a simple auditing procedure. If you plug it in on Q1, it's equivalent to estimating dQ1 dP and using it for bias correction. But the same thing is true if you plug it in on Q2. And the same thing is true if you plug it in on Q3. And so this is very strange because F hat M never got to see any data from Q. It was only using data from P, but it somehow optimally implements transfer learning to any Q such that dq dp is in this Hilbert space ball. So that's the big picture summary. I'm going to have a quick discussion. And because I still have 10 minutes, I'm going to subject you all to the technical results. But it has colors. They're both equations and colors. So I promise it won't be that bad. But a quick discussion before I do that. I intentionally didn't fill up the time so that I could give you the proofs. Anyway, there's no cost of robustness for covariate shift, at least in this sort of Hilbert space type setting. This works for other linear smoothers as well. So random forests technically are not literally ridge regression because of this adaptivity of the basis. But there is this really lovely paper that proved that the weights for the linear smoother version of random forests also converge at a pretty fast rate to dq dp under conditions. There are some interesting algorithmic questions here, because when I say a Hilbert space ball, I'm usually envisioning an infinite dimensional Hilbert space, some type of like flexible powerful regression, which is more in this like strong learning type approach, and not really in the spirit of boosting, which was more looking at like taking these weak learners and building them up on each other. And so there's some interesting algorithmic questions about connecting multi-accuracy and this type of result outside of this narrow estimator that I'm proposing. It also works for other estimates. So I've just been talking about the missing mean, but actually this is more in the spirit of the talk we saw about which statistics can we multi-calibrate, which statistics can we run this estimator on and still get the same result. Well, it's any mean squared continuous linear functional of the conditional expectation. So that is a little bit complicated sounding, but it means that if you want to estimate something like an average derivative, this multi-accurate predictor type approach is going to give you the exact same efficiency results. It will also work. You can just plug this into Christoph's talk. from 2 days ago because he uses the exact same setup. And you actually get, instead of the T learner, you get a variation called the DR learner, which is proposed by Kennedy, just as a numeric immediate result from his proposed estimator, which is also an interesting connection. I won't have that much to say about that because when you're estimating something uniformly, all the math gets more complicated. Means are so nice, very simple. Okay, and behind the scenes is a story about overfitting, which I'm going to talk to you about in the next 5 minutes. Does anyone have any questions about the rest of the talk?
Question. Can you help me understand how fitting ridge gives you like
Yes. So this is the type of likelihood ratio estimation problem I'm claiming Ridge implements. It's equivalent to this simple minimization problem. And it turns out that the solution to this minimization problem is, so you know how Ridge is going to be like, it's basically going to look like X transpose X inverse X transpose Y with your Ridge penalty in there. And then when you apply that to XQ, you slap an XQ on it. The solution to this problem is XQ, X transpose X inverse X transpose. So if you slap a Y on it, it's equal to Ridge. So that's the numerical. The fact that this is equivalent to this is not so hard to see. You just have to plug in. The trick is that you apply Riesz representation theorem.
and does this procedure work well when overlap is a problem?
So you can't get efficiency without overlap because you can't correct the bias.
Lower overlap.
But I'm pretty sure that this is the right thing to do if you have overlap violations because you're not inverting a propensity score. Hey, we had a causal inference question.
So if you're running how sensitive would some of the steps be to this lambda? Sort of the
Okay, yes. I mean, that is really what it comes down to. So, okay. I still have 5 minutes. So hold on to that. That's really important. So why does this whole multi-accuracy hold, even though we're doing this much simpler boosting procedure? So this is the definition. This is like the left-hand side of multi-accuracy for my boosting procedure, where you recall that this is ridge regression on the residuals. If you just use, so this is multi-accuracy over a Hilbert space ball. This thing is exactly equal to this expression, which is the gradient of the squared loss of the residual regression problem measured in the Hilbert space norm. So this is just using the dual norm trick, right? You have a soup over a ball. You should be envisioning that there's a dual norm somewhere that you can swap. And what's the dual norm in the Hilbert space? It's the Hilbert space norm. So everything has this nice form. Okay, but solving least squares loss minimization precisely makes this thing small. And so I have this type of inequality that I can show, for example, which is that when you do the boosting, you have the gradient of the loss of the original estimator, and then you're always going to shrink it. So this is a little bit informal because actually we can just do better by analyzing this thing directly. This is kind of like a cute inequality, but I think the cute inequality helps you get a better intuition for what's going on. We're always overfitting. We're making the gradient of the loss smaller. That means closer to the best fit that we can get. So if multi-accuracy is in this Hilbert space setting, is how aggressively we fit the squared loss, we have this story of overfitting, especially if you fit this with ERM. And when you do boosting, you're always going to get something that's fit like at least as aggressively. And it turns out that this is the right thing to do for Hilbert space regression. That there's all this barrage of results that show if you do RKHS kernel ridge regression and then want to apply it under covariate shift, it's optimal to choose a lambda that's smaller than the one you would choose from cross-validation. So at least to me, that was sort of obvious for when you're estimating an average, because averages wash out variance. And so you want to choose a lambda that's smaller. But the surprising result is that even if you care about predictive mean squared error under covariate shift, you should still use a smaller lambda when you're doing an ArcHS type regression. So there's this weird connection where if you want to be robust to covariate shift in Hilbert spaces, you should regularize less. And that's a little bit in tension with empirical work, which usually shows that when you have covariate shift, you want to regularize more to be robust to it. So I don't have necessarily a solution to why this is the case, but one extreme case of this is interpolation. So ridgeless boosting on the residuals will make this exactly 0. AKA you're doing ordinary least squares in infinite dimensions. And so that's exactly what this quite popular benign overfitting paper studies. And there's been many other situations where people have been setting this gradient of the squared loss to exactly 0 and then studying the resulting estimator. So I've kind of snuck in knowledge about Q in my procedure. Because you fit this with ERM, really to get a totally optimal estimator for a particular target Q, you might need to change the lambda of how much you overfit. And it's going to depend on the size of the covariate shift. But for all of the distributions with the same size of covariate shift, like you can think of that as a shell, you should use the same plugin estimator. Okay, and we're at basically the end. So if anyone has any questions. People want to.
Point where people realize that they're having-
Yeah.
speakers and all the participants. It's great to see so many of you.